here. My gardeners are here today, and where I record is right next to where they are gardening. I don't know how bad the feedback is, but hopefully it's not too bad, and hopefully they won't be leaf blowing right next to my window for too long. Sorry for that inconvenience. They actually aren't supposed to be here on Wednesdays. They're supposed to be here on Thursdays, but things sometimes don't go according to plan. So anyway, good afternoon, everybody. So happy Wednesday, happy end of week 6 of the semester. Just in case you haven't been keeping track of the calendar, we're now ending week 6. So congratulations, you've made it really far into the semester. We are almost at the halfway point. And after the halfway point, that means we're less than halfway to winter break. And winter break means winter break. Normally, I would say, and you guys have, fun vacations and stuff and probably lots of gatherings. But clearly this semester, there's a lot less of that because of, coronavirus. But at least we can look forward to cooler weather, right? At least we're close to cooler weather. That's all I have to say about winter break at this point. Okay. So last we were talking about product rule, and we talked about quotient rule, and we also started to talk about some trig derivatives. So we talked about 2 trig derivatives, sine and cosine. And then I said, hey, because we have these quotient rules, we can actually find the derivatives of the remainder of the trig functions. So, is there a question? Oh, there we go. Sorry. All right. There we go. So getting started, we did tangent and we did cotangent. So these are trig derivatives you're going to want. Normally is my pen not synced? Hold on, let me sync my pen up. Normally, you can do it, pen. Okay. Normally I would tell you need to have these memorized, but because we're not in a situation where, we are in a situation where I'm allowing you to use notes, clearly you don't need to have these memorized. You just need to make sure you know these derivatives. We're going to go ahead and do the remaining 2, and it'll be fun. So kind of how we did for tangent and for cotangent, we can use some of the properties that trig functions have to rewrite them in a way where then we can use quotient rule. So secant is the same thing as 1 over cosine. And we can use quotient rule, which maybe I should write quotient rule over here. If you have a quotient of 2 functions, it's f prime g minus g prime f over g squared. We can use that rule to find this derivative of secant. So our top function is 1, and the derivative of 1, because 1 is a constant, is 0. The bottom function is cosine x, and the derivative of cosine is negative sine x. Apologize about the barking dogs. The dogs also do not like the gardener, as traditional for dogs. Okay, so there's a question in the chat box. Do you think with the extra help we're getting due to this situation, we'll be less prepared for Calc 2 or 3? Would you be less prepared for Calc 2 or Calc 3? So here's what I would say. If you take Calc 2 or Calc 3 in the classroom, chances are you're going to need to do it without notes. There's some teachers who will allow note sheets, and there's other teachers who will not allow note sheets. If you are somebody who thinks that maybe like it might be a problem for you that if you're allowed to use notes here, it might be a problem in Calc 2 or 3, not being able to use notes. You could always do the tests without your notes, or maybe do it without the notes at first and then go back over the exam to make sure that, you with your notes to make sure that everything is right. I don't think it makes you less prepared. I think what makes it harder is that we're in this online setting, and it's just harder to learn in an online setting for a few reasons. Teaching virtually just isn't the most effective form of teaching. I can do my best. I can do my best to provide you with everything I can. It's just not going to ever be as effective as learning in the classroom. And additionally, it's hard to learn at home. Right? It's hard to learn at home watching your computer. I think that's more of the problem than the testing. When I was in undergrad, my calculus courses at the University of Washington did allow a note sheet. So their whole thing is, sure, you can have a note sheet for your exams. However, we're going to make the tests so hard that it's not going to matter if you had a note sheet. Go ahead and have it. We'll just make them really, really difficult. And it was actually quite effective. Having a note sheet helped me study and helped me organize my thoughts, but wasn't very useful during the tests themselves. So I don't think that necessarily having these extra resources makes it so you're less prepared for the other classes, as long as you are doing your own work, taking your own work seriously, trying to do it without the notes to the best of your ability. If you're doing those things, if you're not trying to look for your notes to copy down answers, if you're really doing your best, you're going to be prepared for Calculus 2 or 3. And I think most of you guys are you're doing your very best. And I think your Calculus 2 and 3 professors are also going to understand that you had to learn calculus online. So your Calc 2 and 3 professors hopefully will be understanding, knowing that you guys were put in a situation you didn't want to be put into in the first place. So I think it's going to be okay. I think they'll be a little bit more lenient, just kind of considering everything that's going on. And thank you to the chat box. Thank you for saying I'm doing a wonderful job. I appreciate that. So for next semester, I mentioned this, I think, to one person, and then also at the review session. I am currently 18 weeks pregnant, so I will be giving birth in the middle of next semester. So I will not be teaching calc next semester because that would be unfair to my students to teach calculus and then get rid of them in the middle of the semester and go on maternity leave. So I won't be teaching it next semester, but we do have a lot of really talented instructors who are, but it won't be me, unfortunately. I would be if I weren't pregnant. I would be teaching it, but it's not currently the situation. Sorry about that. Other questions at all? Thank you. I appreciate that. We're very excited. We will both be, so question was about my husband who also teaches math. We will both be going on, he'll be going on paternity leave. I'll be going on maternity leave. So we'll both be taking the semester off about halfway through so that we're able to spend time with our child. But he is teaching calculus this semester, and I think a lot of his videos are posted online. If you'd like, I can ask him if they are posted on YouTube, which I think they are, and I could give you the link to those YouTube videos that he's made for Calculus 2 that you might find useful. You can send me a message on Canvas about that, and I'd be happy to ask him to see if he would be willing to send along his resources. I know it's not the same thing, but it's something. It's something I could offer. No problem. No problem. You all are going to be fine. I promise it's all going to work out fine. I don't think I'm the only instructor who recognizes that you've now had to go through 2 semesters, potentially 3 if you took summer as well, like that, potentially 3 semesters of different learning, of remote learning when you weren't expecting remote learning. I think most instructors are being accommodating to that. I hope most instructors are being accommodating to that and not barking at my students, please. So I think it's going to be really okay. All right. So we'll get back to this question. If you have more questions, feel free to put those in the chat box. I'm happy to answer them. And we're back to leaf blowing and barking. Okay. All right. We have this derivative. We're going to use quotient rule right over here. Hold on. Let me mute I'm going to yell at him. I have a very disgruntled dog over here, giving me a lot of attitude for being asked to lay down. I'm very sorry, sir. Well, now I know I could never bring my dog to class. I mean, I already knew that, but teaching from home has let me really know I cannot bring my dog to class. Alrighty, so going back to this. Here we have quotient rule. We have these derivatives. We have the f, we have g. We took some derivatives. We're going to plug into quotient rule and get our answer for the derivative of secant, which is the same as 1 over cosine. So f prime is 0 times g is cosine x minus g prime is negative sine x times f is 1 and then g is cosine, so we do g squared cosine x quantity squared. So 0 times cosine is 0. Two negatives are going to make a positive, and then sine times 1 is just sine. And then cosine squared would be cosine squared x. Now, here's the thing. Because these are really common derivatives, we actually end up writing it in a different way. So this is the derivative of it, and of secant, technically. But because we're, fancy mathematicians here, it's not enough for us to just leave it like this. Like, we don't want to say that the derivative of secant is sine x over cosine squared x. Instead, as mathematicians, here's what we'll do. And you'll never have to be this tricky. This is just what we're doing once so that we can get the derivative as it's typically written. But technically, this is the same as sine x over cosine x times 1 over cosine x. Would you all agree? Hopefully, cosine x times cosine squared x, sine x times 1, sine x. And sine over cosine is tangent. And 1 over cosine x is secant x. And let me kind of bring it down a little bit. So that's the final derivative that we use, is tangent x secant x. And these will all be summarized on a few pages later. At the end of this section, I think it's at the end of the section. Let me double check. At the end of this section, all of the derivatives that we talked about up to this point will be not barking at people. Lay down. Now, lay down. Toby, down. You're so stubborn. All right. Tangent x secant x, that is the derivative for secant x. Now, I'm just going to tell you that you could do this same process with this cosecant. I'm not going to do it because you've seen me do this process a few times now, and I don't think you need to see me do it necessarily once again. You could try it on your own and try to recreate this, but you're going to get negative cotan x cosecant x. Now, if you're somebody who's potentially like, you're like, I really want to make sure that I am memorizing the things that need to be memorized. I want to make sure that I'm, treating this class the way that it would be if we had to do this without a note sheet. I would say that cosecant is one that you rarely end up like. Instructors will ask you to memorize it, but not be as big about it. I will tell you that knowing, I'm going to go back a slide for a second. I will tell you that knowing cosine and sine is vital. And tangent is vital. Some instructors won't care as much about cotangent, but if you don't know sine, cosine, or tangent off the top of your head, that's when instructors are going to be like, you don't know those three off the top of your head. You should know those three off the top of your head. Cotangent and then also cosecant. If you don't know those ones off the top of your head, they'll remind you and probably not be as annoyed. Secant, you should know though. And I will star those on the last page, which it's page 26, I think. Nope, not page 26. Page 29. On page 29, I would say that in terms of ones that are important and that like your instructors will definitely think that you should know off the top of your head, these guys right here. These guys right here. And then ln. I'll tell you that, so this again is on page 29. This derivative is one, if you forget it, I don't think any instructor is going to be like, oh, I can't believe you don't remember this particular derivative. This one, so base A for the exponential, base B for the logarithm, and then cosecant and cotangent, those are ones that are less like vital. But these four trig, and then basic power rule, derivative of constant, e to the x, and ln x, those are very, very important. All right, so doing some examples with product rule and our new trig functions. So now we have x squared sine x. This is a product rule situation because you have two functions being multiplied together. This is the same thing as x squared times sine x. It's really important that you're recognizing situations that are product rule because it becomes really easy for the brain to just want to take derivatives flat out, to be like, this is 2x cosine x, right? That would be the derivative of x squared and the derivative of sine x. But that's not correct because it's multiplied, so we have to use product rule. Right? So I'm going to call this guy f and this one g, and I'm going to do a little less color coding. Kind of get used to a little less color coding. Right? So f is x squared, f prime is 2x, g is sine x, g prime is cosine x, and then product rule as a refresher. The derivative of f times g is f prime g, it's prime, g plus g prime f. So don't get confused with this f and this f here. I mean, I'm using kind of abusive language, but I'm just using f since we always just use f in this notation. It's not the same f's. Right, so f prime is 2x, g is sine x, plus g prime is cosine x, and f is x squared. Now, typically we don't write the x squared at the very end. Typically we would write the x squared before the cosine. So I'm just going to rewrite my derivative as 2x sine x plus x squared cosine x. And that would be that one. Are there any questions on that? If there's not, I would like you to try out part B. And remember, you can now use the rules that we have for the trig function. So you can use the derivative that I gave you for tangent. You don't have to rederive it, right? So you can use the derivative that I gave you just now for tangent on the previous, I guess, 2 pages ago. And go ahead and do this derivative. I'm going to pause the recording and mute my mic for a second, give you a chance to work it out. All right, let's go ahead and talk about it. So top function f, bottom function g. Once again, quotient rule. F prime g minus g prime f over g squared. So f is x cubed plus ln x. F prime is 3x squared plus 1 over x. G is tangent x. And the derivative of tangent x we found to be secant squared x. So the derivative of k, f prime is 3x squared plus 1 over x times g is tangent x minus g prime is secant squared x. F is x cubed plus ln x all over g squared. So I'm just going to write that as tangent squared, which is the same thing as writing, undo. It's the same thing as writing that. This is the same thing as tangent squared. How did that one go for everybody? Was that one okay? Good, excellent, excellent. Now, I will let you know in the answers to, I think, this section and the next section, sometimes the author simplifies the notes a little, simplifies the equations a little bit. So if you're getting a different answer than the answer that's in the notes, my suggestion would be to like distribute things and see if anything combines together. There's oftentimes not a ton of simplification, just there's a little bit. Somebody said that they wrote x to the negative 1. I'm assuming you meant for this piece right here. Yep, totally fine. Yeah, so if you wrote x to the negative 1 instead of this guy right here, that would totally be fine because 1 over x is the same thing as x to the negative 1. Absolutely. Any other questions, concerns, complaints? All right. Okay, excellent. All right, go ahead and try example C. This guy right here. You can use the derivatives that are from the previous pages, and make sure you're using product rule. Go ahead and do that. And then when you get your final answer, simplify it. Practice simplifying it a tiny bit because it'll simplify just a tiny bit, it will. All right, so I'm going to stop the recording again and mute my mic and then double check that these recordings are actually recording because my husband had some trouble with recordings last night. Now I'm worried that mine aren't recording, so I'm going to double check. All right. I'm not sure if that was enough time or not. It's really hard to gauge time when you're doing this remote. But this is, I guess I'll just kind of go. This is going to be a product rule situation. So your first function f, your second function g, So you have cosecant z as your first function f. The derivative of cosecant is negative cotangent. And important that you put z here because z is the variable. So negative cotangent z times cosecant z. And then g is cotangent z. And g prime is negative cosecant squared z. So for the derivative of our big function, remember this will be f prime g plus g prime f. So we have negative cotangent z, cosecant z. G was cotangent z. Plus g prime is negative cosecant squared z. And then f was cosecant. Prime g, g prime f. So I'm just looking at my notes, trying to figure out, I made an error in my notes and trying to see where my note error is. Okay, there it is. Okay. So anyway, this would be cosecant z. Simplifying this, because it simplifies a tiny bit, you can combine together. Here we have a cotangent times a cotangent, so we could combine those together to be negative cotan squared z times cosecant z. Then this will be a minus sign, and these cosecants combine together as well. So we have cosecant cubed z. Now, that's just an extra step. You don't have to go that extra step. Some instructors feel differently. This is not something that all instructors necessarily feel the same on. But for me, I'm fine with this answer. I'm also fine with this answer. And if you wanted to go even further, you could factor out a negative cosecant z. Just if you wanted to just really be fancy about it, if you're just really like, you know what? I don't think that that's fancy enough. You could factor out a negative cosecant z and you'd have cotan squared z plus cosecant squared z. So that's pretty cool. Any questions on that one at all? Okay. I'm trying to determine in my head if there's like any more cool simplification that could happen from there. And it couldn't get that much cooler from there, unfortunately. It could get a little cooler because you could change the cotangents into cosecants using using sine squared plus cosine squared equals 1, the alternatives of that. But we won't go that far. Something for me to think about later. All right. Let's go here. So we have something going on here. And that something that's going on is that in general, when you have a function, you can take each term of a function. And remember, terms are what's separated by pluses or minuses. So in this case, this is one term. This is a second term. This is not two different terms here because this whole thing is part of multiplication. So this is multiplied by this. So you have two things that are separated, two terms here. And you could take the derivative of each of these separately. However, and you will. However, each of these individually requires product rule. So what we're going to do is we're going to kind of split this up into two pieces. We're going to deal with each piece separately, and then we're going to put it back together in the very end. So essentially what's going to happen, I'm going to call this guy T sub 1 of W, and I'll call this guy T sub 2 of W. And what we're going to end up with when we take the derivative is this will be the derivative of T sub 1 minus, because there's a minus sign right here, the derivative of T sub 2. So we just need to find T sub 1's derivative and T sub 2's derivative, and we'll do them separately. So our first part is e to the W times cosine W. So for this one, our f will be e to the W. The derivative of e to the W is e to the W. G will be cosine W, whose derivative is negative sine W. So the derivative of T1, so T1 prime, remember this will be f prime G plus G prime F. So that's e to the W cosine W. And then plus G prime is negative sine W. And then F is e to the W. Simplifying that just a tiny bit, the first part will stay the same. The plus sign turns to a minus because of this negative sign, and then I'm just going to move the e to the W in front just because that's more standard to have the e to the W's or the e to the X's in front of the trig. Okay. And that is for T1. That is for our first part. And now we're going to do our second part, our T sub 2 of W, which is W squared plus 1 times secant W. Our F is going to be the W squared plus 1, whose derivative is 2W. Derivative of a constant is 0, so W squared is the only thing we take the derivative of. For secant, our derivative is tangent W secant W. Or secant tangent. Either direction works. You can say tangent secant or you can say secant tangent. It is the same thing either way. To take that derivative, once again product rule, so f prime G plus G prime F. So we have 2W secant W plus tangent W secant W, that would be G prime. And then F is W squared plus 1. So, I mean, there's not a ton of cleaning up I can do here. If you want, you can bring this in front and kind of remove some parentheses. So you could do 2W secant W plus W squared plus 1 tangent W secant W. I mean, there's really not a ton of cleaning you can do here. And then as I said, the derivative of our big function this guy right here is just going to be combining together these two derivatives. So t1 prime, that's e to the w cosine w minus e to the w sine w minus, and then because there's a minus here, either you need to put big parentheses or you need to distribute the negative and make that a negative as well. I'm just going to opt for big parentheses. And I'm going to write down this whole derivative here. And that, my friends, is the derivative of that function. So what you end up with derivatives is a lot of these derivatives end up looking really, really nasty and really, really long. And it's not like, they think when you look at the answer to these, they look a lot more complicated than they actually are. You just have to break it down into their different components, organize your thoughts. I think organizing your thoughts is really, really important on these. And it will all come together. But they do look intimidating. I know these answers look very intimidating. Remember that you have all these exercises at the end of the section. All those answers are now posted. So if you look at the announcements, I made an announcement that they're posted. And additionally, I posted that free textbook that should also have a section on product and chain rule. If I double check real quick. Let's see. I think I put it under resources. And it's at the very top of the resources page, that free textbook that I found on OER. And then I'm just going to search the words Control F product rule. Yep, so in the free textbook online, on the Apex Calculus textbook that I posted on the resource page, product rule and quotient rule are section 2.4. On page 89. It's page 89 of the textbook, but it's page 97 of the PDF. So they have a whole section on that, and they even go through the proof, which is really cool. If you're somebody who plans on going further in math, you should definitely look at the proofs of quotient and product rule. Super, super neat. Wish we had time to go through this, but they have a lot of exercises, what I was getting at. They have a lot of exercises, and then all the answers to the odd exercises are at the end of the textbook. So if you need additional practice there, there's always that, along with the exercises provided to you in the guided lecture notes at the end of each section. All right. Cool. Excellent. So now let's talk about higher order derivatives. So higher order derivatives are essentially taking a derivative of a derivative. That's all you really need to know about this term. This really means taking a derivative of a derivative. Oops, that looks like derivative. So a first order derivative is just your regular derivative, right? We've done that. But then if you take the derivative of f prime, we call it f double prime. Put a little space there, double prime. And that's just taking the derivative of f prime. If you take the derivative of f double prime, you end up with f triple prime. But then you can see how quickly the primes would get out of control if you were taking like the 15th derivative. Like no one's going to sit there and count up all your primes to see that it's the 15th derivative. That would be very, very annoying. So after 3 derivatives, so after you've taken the derivative of the second derivative, you have f triple prime or y triple prime. Then we just start using parentheses. So we don't want to do it without the parentheses because then you wouldn't know it's a derivative. You'd think it was just raised to the 4th. So you put it with parentheses and a 4, and that means the 4th derivative. Because counting primes won't work anymore. And you can do that for any number. So anything past 3, you're putting the number of derivative it is in a essentially exponent with parentheses around it. So let's talk about what that looks like. So we have this function f of x equals x cubed minus 11x squared plus 3 to the x, not 3 to the x, 3x plus 2. Find the 4th derivative. So we would start by finding the first derivative. And the first derivative would be 3x squared minus 22x plus 3. To get f double prime, we take the derivative of f prime. So f double prime of x would be 6x minus 22. Oops, that's not what I meant to do. To get f triple prime, look at me being sneaky here. To get f triple prime, you take the derivative of f double prime. So I start with f double prime and I take his derivative, which would just be 6. Then going even further and still being tricky and avoiding rewriting things. To get the 4th derivative, that doesn't look like a 4 to me. You take the derivative of f triple prime. And the derivative of a constant is 0. And then down here, just kind of a fun fact. So if you have a polynomial of degree n, for instance, this polynomial was degree 3 because that's the highest degree. So the highest degree is the degree of the polynomial. And you take the n plus 1th derivative. Well, I mean, you can kind of test this out. Like if you have x to the 6th as your original function, right? The first derivative, 6x to the 5th. The second derivative, so in this case, n is equal to 6, because that's the degree of your polynomial. So n plus 1 would be the 7th derivative. So if we go all the way to the 7th derivative here, this number is going to get a little out of hand. But we have 30x to the 4th, third derivative. We have 120 x cubed. The 4th derivative, 360 x squared. The 5th derivative, 720x. The 6th derivative, 720. The 7th derivative, 0. So if you have a polynomial and you take its highest degree, if you take derivatives that are one more than its highest degree, you're going to end up with 0 every time because everything is going to end up disappearing. So the answer to this question, if f is a polynomial of degree n, what is its n plus 1th derivative? The answer is 0, just because everything ends up disappearing. So just kind of a cool fun fact. All right. So here we have an example, and we're asked to find y triple prime for y equals x cubed ln x. So we need to do this in stages. We need to find y prime, then we need to find y double prime, then we need to find y triple prime. And we kind of need to organize our work because it can get kind of confusing. So starting with finding y prime. We need to do product rule here. So we have f and g. So f is x cubed. So f prime is 3x squared. G is ln x. G prime is 1 over x. We're using product rule here, so f prime g plus g prime f. Right. So f prime 3x squared, g is ln x, plus g prime is 1 over x, and then f is x cubed. Here's the secret. Here's the trick. Simplify at every step. Simplify after each derivative to make your life easier. I promise you it will make stuff easier. For instance, you might think you need to use quotient, or not quotient. You might think quotient rule. You might think quotient and product rule here. However, 1 over x times x cubed, that's the same thing as x cubed over x, which is just x squared. So y prime is really 3x squared ln x, that can't be simplified, plus x squared. So don't make things harder on yourself than you need to. Let me make a little more room before I make that line. So next we're going to work on finding y double prime. This first part is going to require product rule. This first part requires product rule. This second part, we can just take its derivative because it's just being added. So we're really going to kind of deal with this separately. So finding the derivative first of this guy. We'll call this guy f and this guy g. So f is 3x squared, which means f prime is 6x. G is ln x, so g prime is 1 over x. So the derivative of 3x squared ln x, which is not the full derivative, right? That's just this first part of the derivative of the derivative. Please don't. F prime g plus g prime f. So f prime, 6x. G is ln x. Hold on. Oh, that dog. Okay. Can you hear me now? Okay. Hopefully you didn't hear me yelling at my dog. Oh, could strangle you right now. All right. F prime g plus g prime f. So g prime is 1 over x, and f is 3x squared. Which this second part can be simplified. So this part right here could be simplified. The x can cancel with one of the x's there, and you get 6x ln x plus 3x because one of the x's canceled. So let me kind of extend this squiggly line. So then taking this guy, I'm just going to rewrite him. I'm just going to rewrite y prime was equal to 3x squared ln x plus x squared. So for y double prime, the derivative of this part here is the 6x ln x plus 3x. So that's that derivative, and then plus 2x for this part of the derivative. As you can see, there's some stuff that can be combined together again. So y double prime, so this 3x and this 2x can be combined together, so you get 6x ln x plus 5x. We have one more step to go, and that's doing that third derivative. So let me label these 1, 2, 3, finding y triple prime, our very last step. I want you guys to try this one. All right, so here's your y double prime. I want you to find y triple prime. I'm going to put it on pause, give you a second to do that, and then we'll come back. All right. All right. So I'm not sure if we're done yet, but I'm going to go ahead and at least start with writing the answer. If you want to still finish it yourself, if you're still working on it, you can put me on mute and then just kind of check your answer. Not mute. You can turn off your sound and then check your answer. So it's kind of the same idea as the before. You have two different parts that you're taking the derivative of. So for the 6x ln x part, this is going to be product rule. So we have an f and we have a g. So our f is 6x, our f prime is 6, our g is ln x, and our g prime is 1 over x. So the derivative of 6x ln x, right, f prime g plus g prime f. So f prime is 6, g is ln x, plus g prime is 1 over x, and f is 6x. these x's will end up canceling, and you end up with 6 ln x plus 6. So coming back to our original y double prime was 6x ln x plus 5x. For our y triple prime, the derivative of this part was 6 ln x plus 6. And then the derivative of 5x is 5. And this 6 and this 5 can combine together. So your total y triple prime, 6 ln x plus 11. So the kind of key thing with our triple, our double, triple, just higher order derivatives, just making sure that you combine things when possible. It really will make your work a lot easier in the end. Sometimes that means factoring stuff out. Sometimes that means like simplifying polynomials. It's a little bit different for each problem, but that would be my suggestion. Are there any questions on that problem, which probably needs a lot more room than it has? Right. So if we go on to the next one is just finding the second derivative of g of t. So this d squared g over dt squared, this is just g double prime. Oops. Let's make that look better. G double prime of t is what we're looking for. So let's try this one. So we'll start with finding g prime of t. This is a product rule. So our f is 5e to the t. F prime is still 5e to the t because e to the t's derivative is himself. For g, we have sine t, and g prime would be cosine t. So g prime of t, and by g prime, I mean, I'm talking about this g. Like I said, we have abusive notation sometimes, but we'll just go with it. So it's f prime g plus g prime f. F prime is 5e to the t. G is sine t plus cosine t, so that's g prime, times f, which is 5e to the t. Now, you could just take the second derivative from here. However, notice if you're doing that, you're going to do product rule here and product rule here. You'll be doing product rule twice, which you can do. However, we can be better. We can be trickier than that. And the trick here, like I said, simplifying, but in this case, simplifying means factoring. So notice that these guys both have a 5e to the t in them. You can factor the 5e to the t out. And if you do that, you'll have 5e to the t that comes out front. And then with the first term, you have sine t and then cosine t. And just think, it would get you back to this point here because if you distribute, you have 5e to the t sine t. Here you'd have 5e to the t cosine t. So it's the same thing. But now, when you go to do your second derivative, you've already factored it, so you only have to do product rule once as opposed to twice. So you can do it with this, just like you could do some really nasty derivatives with this guy up here. You could make this into a double product rule with a quotient rule in there. You can make it really nasty, or this trick makes it so you're now only doing one product rule. So let's find g double prime of t. Again, product rule, but we only have to do it once. So we have f and g. Our f is 5e to the t, who we already discussed had the derivative 5e to the t. G is sine t plus cosine t. So g prime will be cosine t. And then this will become plus negative sine t, so I'm just going to write minus sine t, because that's the same thing as plus negative. So product rule, f prime g plus g prime f. F prime is 5e to the t. G is sine t plus cosine t, plus g prime is cosine t minus sine t. And then f is 5e to the t. Now, this, we only needed g double prime, so, technically we could just say, hey, that's our answer. But if we did need to go further, which, again, we don't need to here, but if we did need to go further, we could say that there's 5e to the t in both of these. So that 5e to the t could be factored out. So you'd have sine t plus cosine t that came from this part right here, plus these guys, cosine t minus sine t, because we pulled the 5e to the t out of them as well. And then your sine t's cancel. So you have sine t minus sine t, and then you have two cosine t's. So you would get 5e to the t times 2 cosine t, which then the 2 and the 5 can multiply together, and you get 10e to the t cosine t. So just fun fact that it does simplify more. That's still g double prime. This is not g triple prime. This is still g double prime. Like I said, this is a fine answer, but if you wanted to go a step further, the simplification, you could either distribute this, the 5e to the t, and then combine it all together, or you could pull the 5e to the t out, combine these terms together. It simplifies, and then we get 10e to the t cosine t, which makes your derivative a lot nicer if you're taking the third derivative there. And there's a challenge problem down there for you to think about. The answer's given, but something to think about why that works. Questions or comments on that one? Okay. So thinking back to physics, once again, so we learned that the derivative of the position function gives us the velocity function. So up to this point, what we've said that you have this position function s of t, and that if you wanted the velocity function, you just went ahead and took the derivative of the position function. Cool. But now that we have multiple derivatives, we can talk about the acceleration function. And the acceleration function, which we give the name a of t, is the derivative of the velocity function, i.e., it's the second derivative of the position function. So the acceleration function is talking about how fast the speed is changing. So how fast are you getting faster, or how fast are you slowing down? It's not your actual speed, it's the change in your speed. For units, with the position function, you use distance units, right? Like feet, meters, centimeters, miles, inches, those sort of things. For the velocity function, your units were distance over time, so like feet per second, or miles per hour, or meters per minute. With your acceleration function, the units are distance over time squared. So that would be something like feet per second squared, or miles per hour squared, or meters per minute squared. Essentially what it really is it's feet per second per second. And then it simplifies to feet per second squared. So it's how many feet per second you are getting faster or slower per second. The rate at which your speed is changing. So if we have a particle and we have its position function, and t is measured in seconds and s is measured in feet, find the velocity and acceleration functions. So to find the velocity function, we take the derivative of the position function. So 4 times 1/4 is just 1. So that would be negative t cubed, because the negative will stay, but the 1/4 and the 4 cancel. 3 times 3 is 9, so we have plus 9 t squared, and the derivative of 7 would be 0. For the acceleration function, I take the derivative of the velocity function, which is right here. We just found that. So that derivative would be negative 3t squared plus 18t. We're not putting units, by the way, on this because we're not, the function itself doesn't need units. It's when you have an actual answer. So it's if I'm plugging in a time value, that whatever answer I'd get, I would put units on that. The next question is find the intervals during which the particle is accelerating, i.e. a of t is greater than 0. Now, I can't think about how to spell the word decelerating, but the opposite of accelerating is decelerating. So you're, don't make fun of my spelling, by the way. I did math, not English. Can't make fun of me. But accelerating means your acceleration is growing, whereas deceleration means that your acceleration is slowing down. So your speed is slowing. So accelerating is your speed is getting higher. You are going faster. Your speed is getting to go faster. It's not staying stagnant. You're going faster. And decelerating means that your speed is going slower. Your speed is getting slower. You are slowing down. So accelerating is speeding up. Decelerating is slowing down. So we want to know when the acceleration is increasing, when the acceleration is positive, because that's when we are accelerating. That's when we are speeding up. So we have this acceleration function, and we're told to set it greater than 0. This right here is a non-linear inequality, which means we need to factor it and set up a number line. So I can factor out a negative 3t, and then I have t minus 6 greater than 0. If you set negative 3t equal to 0, you get the 0 t equals 0. T minus 6 will give you the 0 t equal to 6. Normally on a number line, we have the arrow that goes off this way, but because time won't go less than 0, we always have our time as being positive. My number line is going to start at 0, and then I will also use this 6 here. And I split up my number line. I choose test points, so I'll choose t equals 1 and t equals 7. And I'm plugging these test points into both of these components. So if I plug in 1 to this piece, right, negative 3 times 1, that's a negative number. Whereas plugging it into the second piece, t minus 6, 1 minus 6, that's a negative number. So they're both negative. And then two negatives make a positive. Right? With 7, we do the same thing, plugging 7 into here. Negative 3 times 7, that's a negative number. 7 minus 6, that's a positive number. A negative times a positive is a negative. Greater than 0 means you want the positives. So that would be this interval here. So our answer would be the interval from 0 to 6. And then in terms of velocity and acceleration, which let's keep those functions on the screen, what is happening to the particle after 8 seconds? So if we plug in 8 seconds to both the acceleration and the velocity function, so plug in 8 to velocity, that's negative 8 cubed plus 9 times 8 squared. This should come out to be 64. And then the units here, if we look back, we have feet and seconds. But the question asked us to describe what's happening. So at 8 seconds, we plugged in 8 seconds to the velocity function. At 8 seconds, the particle is moving at 64 feet per second. Plugging it into the acceleration function, plugging in 8 to the acceleration function, which is this guy here, negative 3 times 8 squared plus 18 times 8 should come out to be negative 48. And then our units would be feet per second squared. So that means, remember, accelerating is when your acceleration is positive. If your acceleration is positive, you are accelerating. If your acceleration is negative, you are decelerating or you are slowing down. So if you have a negative, acceleration, you would say at 8 seconds, the particle is slowing down at a rate of 48 feet per second squared. And you might ask me, hey, wait, what about that negative right there? So if I was simply asked what is A of 8 and not asked to describe what's happening, I would say A of 8 is equal to negative 48 feet per second squared. I would keep that negative and I would say bam. However, because I'm saying slowing down here, I'm already saying the words slowing down implies the negative. So you wouldn't want to, you would be negating it by saying slowing down at a rate of negative 48 feet per second squared would be like you're slowing down negatively, which would be speeding up. So the answer, the acceleration is negative, right? If you said that at 8 seconds the particle is accelerating at a rate of 48 feet per second squared, that would be, or negative 48. If you said accelerating at negative 48 feet per second squared, that would be correct. But saying that you're slowing down at a rate of negative 48 feet per second wouldn't be correct because the negative already implies the slowing down part. Right, questions on that last problem at all? Okay. I'm going to just double check. To make sure. Okay, cool. So you have homework for 2.3, which is the section we just finished, but 2.4 isn't included in the homework, which is good because we're kind of a little bit behind. We are going to start 2.4, but we're not going to get through 2.4 today. So the derivative rules up to this point are given here. Something, if you're looking at memorizing, there's a note at the bottom of the page here. For the derivatives of the trigonometric ones, the ones that end up being negative all start with a C. So if it starts with a C, it ends up with a negative in front of it. So it's just something to kind of keep in mind. The cofunctions, because they're called cofunctions, cosine, cosecant, cotangent, they all end up with a negative in front of their derivative. And they also kind of match up because secant and cosecant are kind of like brethren because secant is 1 over cosine and cosecant's 1 over sine. So they're like siblings. And their derivatives kind of match, right? Secant tangent, whereas cosecant is cosecant cotangent. And then cotangent and tangent kind of match, right? Secant squared, negative cosecant squared. And then sine and cosine kind of match because cosine, sine. Any questions at all on section 2.3 on the product rule, quotient rule, higher order derivatives before we move into the next section, which is chain rule, which is a hefty section. All right. So these are the questions from this section. All right, then here we are in unit 2.4, the chain rule. The chain rule is it's a hefty section. It's a really, really important section, but it is hefty. It takes a little getting used to. I'm going to give you a bunch of different ways of thinking about chain rule, and hopefully one of these ways sticks out for you. We only have 20 minutes to talk about it, so I won't get super far into it, but hopefully we can at least get through a few examples. So chain rule has to do when we have a composition of functions. So a function inside of a function. An example of a composition of functions, something like down here, you have this inside function being raised to the third power. That's a composition of functions. Right now, the way that we would take care of this, we would have to FOIL the whole thing out, or we'd have to write it as x squared plus x minus 1 times x squared plus x minus 1 times x squared plus x minus 1, and then use product rule twice. It would be pretty nasty, but there's going to be a faster way of doing it once we've talked about chain rule. So I'm going to talk about the formal notation of it, and then I'm going to break it down. Essentially, you have an outside function, which in this case would be f, and then an inside function. So the inside function gets plugged into the outside function. And what it ends up being is that the derivative of the outside times the derivative of the inside. That doesn't make a lot of sense until you've practiced it. Formally, if you have this composition, the derivative is the derivative of the outside times the derivative of the inside. And this looks weird because it's like you almost feel like it should be f prime of x times g prime of x. You're like, what's going on with like this composition thing here? And that's going to take some explaining. That's going to take a few examples to get used to. So I will explain it, but that's formally what it is. That's formally what the chain rule says. There is an alternative notation that gets used. We will end up using this notation a lot during the related rates section, which is a little bit later. But the Leibniz notation, so this is not Leibniz notation. Is it Newtonian notation? I don't remember whose notation this one was. But Leibniz notation is that dy dx, if you have a composition, so f of u and then u is this function, same thing, same idea, is dy du times du dx. And I'm going to go through both notations and how to use both of them. This just requires practicing. You flat out will not get good at chain rule unless you practice. There's just no way around it. There's no secret way where you get good at it from watching a YouTube video or you get good at it from watching me do it. There's just no secret to it. I make the comparison of learning math to weightlifting a lot. You can go to the gym and you can look at the weights and you can watch people lifting weights and you can watch YouTube videos on people lifting weights and then learn, go take a bunch of anatomy and physiology classes and learn about how the body builds muscle. And you can learn all those things and be really smart about it, but you're not going to be an ounce stronger until you've actually gone to the gym and lifted a weight for yourself over and over and over again. You can watch as much as you want, but you're not going to get good at math unless you try. And it's especially true for chain rule because the idea is very, very foreign. Product and quotient rule are actually a lot more they're a lot easier to grapple with than chain rule. And you're going to see that in a moment. But it's going to feel confusing at first. And it's going to feel a little frustrating at first. And it's really, really important that you practice this. I cannot emphasize that enough. I mean, all I can do is tell you, I can't, you can lead a horse to water, but you can't make him drink. I can tell you that it is important to practice and that you will not be good at this without practice, that it will remain confusing to you unless you devote yourself to practicing it. And that's all I can say. All right. So moving forward then, we're going to do some chain rule here. So we're going to use both the composition method and Leibniz method to kind of show you the two different methods. So here we have h of x is equal to sine x squared. All right. So with the Leibniz method, they basically say, hey, you're going to have an inside function, you'll call it u, and then you take the derivative of y with respect to u, and then you take the derivative of u with respect to x. So in this case, the inside, we would call him u. So u is equal to x squared. But then our y becomes sine of u. So we're replacing the x squared with a u. the first part here. So dy dx is equal to dy du. So take the derivative of y with respect to u. Maybe I'll make these different colors. Maybe I'll make maybe that'll help a little bit. I'll make these different colors. So the derivative of y with respect to u. Okay, and WRT means with respect to. Basically saying that's what the variable is. So with respect to u. So taking this derivative, well, derivative of sine is cosine, so this would be cosine u. Then taking the derivative of u with respect to x. So this is my u, and the derivative of that with respect to x would be 2x. However, this won't be our final answer because our final answer has a u in it, and our final answer should have no u's in it. So you use the fact that u was x squared to plug in for there. So you get cosine of x squared times 2x, or 2x cosine of x squared would just be rewriting it. So with the Leibniz method, you are identifying an inside function and an outside function, taking the derivatives separately, and then replacing u at the end. This works okay, but as you start to get chain rule nestled within chain rule nestled within chain rule, which we will get into, this method becomes a little less sustainable. So this was the Leibniz method. Oops, let's see. For the composition method, we determine an outside function and an inside function. So again, we're still looking at this sine of x squared function here. So the outside function is just, so the outside is sine, and then we just leave the inside alone. So we have sine of x squared as the outside function. And the inside function is x squared, because x squared is what's on the inside. So when you go to take the derivative, you leave the inside alone. When taking the derivative of the outside. So the derivative of the outer function, the derivative of sine, is cosine. So you'd have cosine and then leave the x squared alone. That's the derivative of the outside. And then the derivative of the inside function, x squared, is 2x. Which is the same answer we got here. So let's go ahead and see it again, because it's just, you're just going to need to see it again and again. It's what's going to need to happen. So for Leibniz method, if we have the function k of x equals x squared plus x minus 1, you're essentially finding this inside function first, and we're going to call that guy u. So our u is equal to x squared plus x minus 1. And our du dx, so the derivative of the function u with respect to x, just taking that derivative, is 2x plus 1. Now, since we called that thing u, the thing that we call y is what happens when you replace the inside with u. Right? So this would become u cubed, because the inside would become a u. The derivative of y with respect to u, just you're taking the derivative of u cubed, is 3u squared. So dy dx is equal to, and maybe I'll color code this, dy du times du dx. Dy du was 3u squared, right here, and du dx was 2x plus 1. But you can't have any u's in your answer, so you're replacing this u right here with x squared plus x minus 1. So you end up with 3 x squared plus, I wanted to make this black, 3 parenthesis x squared plus x minus 1 squared times 2x plus 1. And that's my final derivative. So this u right here just became what it originally was. So all I do from this step to this step, the 2x plus 1 stays alone. I'm just replacing u with its original form here. I'm putting it in parentheses. For the composition method, you're first determining the inside function, which is the same thing that you did with Leibniz, but you called it u instead. But for the inside function, you're looking at x cubed, there's not x cubed, x squared plus x minus 1. And for the outside function, that just ends up being the whole function. So you include everything, including the cube. So the outside function is x squared plus x minus 1 quantity cubed. So k prime of x, I'm going to write it out first, is going to be the derivative of the outside multiplied by the derivative of the inside. So with the derivative of the outside, like I said, you leave the inside alone. So I would just treat the inside like I'm not pretending it's not there. I would take the exponent down in front. So I have 3 x squared plus x minus 1. I'm leaving it alone. And then I lower the exponent just like I would do with power rule. And then I would take the derivative of the inside, which would be 2x plus 1. So my derivative is 3x squared plus x minus 1 times 2x plus 1. So I have a few minutes left. I'd like to do at least one more example. This takes practice. I will repeat myself. It takes practice, it takes practice, it takes practice. I'm going to start solely using composition method because as we get further into this, the composition method is going to make the most sense. But if you want to use this Leibniz method, it can help you kind of parse it down because you can see that this isn't that different than this, right? This has a few extra steps involved, but like this, they're not very different. If you start with the Leibniz method, you're going to understand the process well enough to transfer to the composition method. So it's okay to start here and move here. It's just that this Leibniz method isn't going to be sustainable for very long as we start to get into more complicated functions. So let's do a derivative. So first of all, we have p of x is equal to the fourth root of 2 minus 9x, which we can rewrite as 2 minus 9x raised to the 1/4 power. So the outside function is just this whole thing. Just 2 minus 9x to the 1/4 power. The inside function is just the inside part. So taking the derivative of p, for the derivative of the outside, you're using power rule. Bring the 1/4 down, leave the inside alone, and then subtract 1 from the exponent. So 1/4 minus 1 is negative 3/4. That is the derivative of the outside. This gets multiplied by the derivative of the inside, so the derivative of 2 minus 9x, which is just negative 9. If you wanted to be real fancy here, you could combine this negative 9 with the 1/4, and you could make it negative 9/4 2 minus 9x to the negative 3/4 if you wanted to be fancy. So we have 1 minute left. I think what I'm going to do is I'm going to go over my time enough to do parts B and C. If you have to leave now, that's fine. I'll have the video posted later so you can come back and watch those remaining 2 problems. But I am going to do those now. So if you need to leave, that's fine. Just please go back into the video that I post and watch me do these ones. All right, so I'm going to go ahead and do part B then. This one is going to require us using product rule because we have 2 functions, one function here, being multiplied together. So this is a product rule situation. So our first function f will be z to the 5th, and his derivative is 5z to the 4th. G is the function 1 minus 3z raised to the 2/3. This is a very similar situation to what we had right here. Right? So for g prime, we start with the derivative of the outside. So we're just taking this whole function and doing power rule on it. We'll take the 2/3, put it in front, leave the inside alone, and then subtract 1 off the exponent. So we have negative 1/3. That's the derivative of the outside. The derivative of the inside is referring to the derivative of 1 minus 3z, and that derivative is negative 3. Now, if I want to be a little bit concise here, what I can do, this negative 3 would get multiplied up with the 2/3. So this guy and this guy. If you have 2/3 times negative 3, this is negative 6 over 3, which is negative 2. So you could simplify this to negative 2, 1 minus 3z to the negative 1/3. Sometimes it's just nice to simplify. I mean, you can leave it spread out like that, but sometimes it's just nice to simplify it. Just so you have, oh, I'm muted. Let's see. Now? Can you hear me now? Testing, testing. Testing, testing, testing. So I don't know where it glitched at. So I don't know at what point. So maybe I'll just kind of re-explain what was happening here. So we're doing product rule. So we have this guy for F, we have this guy for G. And for G, the outside function is just this entire function. So we have to do chain rule here, just like the one above. And we take the 2/3 down just with power rule. So we take it down, we have 2/3 in front, leave the inside alone, and then subtract 1 off the exponent. So you have 2/3, 1 minus 3z raised to the negative 1/3. And then for the inside part, 1 minus 3z, we take that derivative and we get negative 3. Now, you can leave it like this. It's just a little bit more spread out, and that's totally fine. You can totally leave it there. But if you want to combine it a little bit, just because it's nice, 2/3 times negative 3 ends up being negative 2. So you could replace 2/3 times negative 3 with negative 2 instead. So now I have f, f prime, g, and g prime, and I'll be good to take my derivative. Sorry about that confusion there, guys. So big F prime, right, is going to be f prime g plus g prime f. F prime is 5z to the 4th. G is 1 minus 3z to the 2/3. Plus, now I'm going to put minus here. I'm going to put minus because I would be doing plus this, but plus and negative would be the same thing as just, just doing a minus. So minus 2, 1 minus 3z raised to the negative 1/3. And then times f, which is z to the 5th. And that would be your derivative, which could be simplified further, but I'm not going to, I already simplified a little bit. I'm not going to simplify it anymore. And by simplify, I mean, you could move the z to the 5th in front here, and you could factor out a z to the 4th if you really, you could factor some stuff out, but it wouldn't really be worth it. You would just leave it like this, please. Doing any more simplifying than simply like this type of simplifying, or some of the other simplifying we've done, doing anything else just makes it harder for me to grade. So for instance, this could be really, really obnoxiously simplified into something completely different. Just don't do that, please. It makes it really, really hard for me to grade, and it makes me suspicious that you used a program, because programs will simplify them in a way that I wouldn't expect students to. All right, so for the next one, last one I'll do for the day, sine to the 4th x over x cubed minus 8. So we have to do quotient rule here, and I want to talk about this numerator, but we're going to do quotient rule. And our top function is sine to the 4th x. I want to talk about that because this is a derivative that I will give on an exam inevitably, either sine or cosine, and inevitably people will get it wrong. And I'll tell you I'm putting it on an exam. I'll tell you right now that I'm going to put it on the exam. You're not going to get away without seeing it. You're going to see it on either this exam or the next exam or the final or the third exam. Wait, that is the third. See, this exam, next exam, or the final. You might see it on all three of the next tests. This is so important for you to know. For sine to the fourth, this is the same as sine of x raised to the fourth power. You use chain rule on it. You use chain rule on it. So for f prime, the whole thing is the outside function, right? So taking the derivative of the outside function using power rule, bring the 4 down in front, right? And then sine of x, leave the inside alone, and then lower the exponent by 1. That's the derivative of the outside. Multiplied by the derivative of the inside. So the derivative of sine x, which is cosine x. I'm going to rewrite this sine x cubed back in this kind of formation. So I'm just going to write f prime is equal to 4 sine cubed x, just because it's a more compact way of writing it. And then g for our quotient rule is x cubed minus 8. So g prime will be 3x squared. So I'm using this f prime, this f, this g, and this g prime to find y prime. Quotient rule, f prime g minus g prime f all over g squared. F prime is 4 sine cubed x cosine x. G is x cubed minus 8 minus g prime is 3x squared, and f is sine to the fourth of x. So if you want parentheses on that, I could also put parentheses on that just to kind of separate them for your viewing pleasure. All over g squared. So g was x cubed minus 8 quantity squared. And that whole giant thing, that beautiful giant thing right there, is the derivative. So we'll get back to doing even more practice of this on Monday, and hopefully that'll all make a little more sense come Monday. Please practice it over the weekend. It's not part of this homework that's due this weekend, but it will be part of the next homework, and it helps to just kind of practice. I think that's all I have to say. If you have questions, comments, concerns, please send me an email. I'm hoping to start grading the exams today. I'm hoping they'll be graded by the start of next week, and that way you guys have them to start correcting. I'm just not sure how long it's going to take me based on how the exams were uploaded. So hopefully it doesn't take too long. I'm not sure. Other than that, have a fantastic weekend. Thank you for sticking around an extra 11 minutes for me. Email me with your questions.